We now have the chore of trying to figure out how to actually write a recursive formula. No longer taking a formula and just writing the terms of it, but how do we write that formula given a sequence of numbers? Well, in order to do that, you need a few things. You need to know where you're starting. You need your a sub 1, and then you need to know, how do I get to the next term? That's it. You just need to know, where do I start? How am I getting to the next term? We can lay out our a sub 1 pretty easy. 23. That's the first term in our sequence here. 23, 29, 35, 41. Now, let's take a look and try and analyze, how am I getting to the next term? Here I'm adding 6. I would first check, am I just adding a number? Here I'm adding 6. Here I'm adding 6. Hey, it sure looks like I'm just adding 6 to get to each of the next terms. I could, if the addition seems different from each term, check the multiplication. Do I multiply by some number to get to the next one? But here, it's just adding. So this is nice. To get to the next term, I just add 6 to the previous term. I can write this as a recursive formula. So I can write a sub n is equal to the previous term plus 6. How do I get to the next term? I just add 6 to it. That's all I do to get to the next one. So my recursive formula is just a sub n minus 1 plus 6. However, I need to know the starting point. So when I write this recursive formula, you must include your a sub 1 because you need to know where to start. So I say my rule is a sub n is equal to a sub n minus 1 plus 6, such that, or including that, a sub 1 is equal to 23. Because then anyone reading that formula will know, okay, I just have to start at 23 and then add 6 to it to continually get my next terms. Notice, how am I getting to each term? I'm just adding a set number. Does that make you think of anything? Arithmetic? This is an arithmetic recursive sequence. So a recursive sequence, it's just a type. It's a type of sequence that the formula relies on the terms before it. And it can be arithmetic because it's increasing by a set 6. Each term has a common difference of 6. So it's an arithmetic recursive formula. Next idea. Write a recursive formula for a sub n equal to 2n minus 4. Let's draw a distinction. This is the type of formula that we have worked with before, and we call it an explicit formula. That's because it does not mess around with what it's trying to tell you. How do you find the 15th term? Just plug in n equals 15 and boom, you get it. With a recursive formula, you're going to have to find the first 14 terms and then find your 15th term. So you got to go through all 15 terms. So it's a little more cumbersome. But for practice, we're going to figure out, how can I convert this explicit into recursive? Well, first, we have to figure out what our a sub 1 is, because remember, we always need a sub 1 with our recursive formulas. So let's plug in the formula. It's 2 times 1 minus 4, which is equal to negative 2. So I know where to start. Now let's lay out the first few terms and we can come up with, how do I get to the next term? So what's a sub 2? Still using the explicit formula. A sub 2 is equal to 2 times 2 minus 4, which is 4 minus 4 is 0. A sub 3, plug in 3 for n, 2 times 3 minus 4. Looks like I get a 2. Let's do one more and then maybe we can analyze the pattern. A sub 4 is equal to 2 times 4 minus 4, which is equal to 4. Lay out my terms. I go negative 2, 0, 2, 4. How do I get to the next one? Well, it's not so difficult. I just add 2. The pattern is just add 2. Add 2 to the previous term. A sub n is equal to the previous term plus 2, so long as you start at -2. So notice once again, my recursive formula depends on the previous term, and I know where to start. I have to include that a sub 1 along with my formula. So whoever reads that, he's got to know his starting point. It's like the maps at the mall. You have the "you are here," and then you can find where you're going to buy your fancy shoes. But you got to know where to start in order to find your fancy shoes. And that's a recursive formula. One more. Write an explicit formula for a sub 1 is equal to 84 and a sub n is equal to 1.5 times a sub n minus 1 n greater than or equal to 2. Now we're going from recursive to explicit, going the other way. Oh, this is fun, practicing going every which way. We're going to be masters at recursive. Well, a sub 1 is equal to 84. Again, let's lay out the first few terms and see if we can't identify the pattern going on here. And a sub 2 would then be 1.5 times the previous term. And so then we get 126. A sub 3 is going to be 1.5 times the previous term, which is 126, and we get 189. A sub 4, sound like I'm repeating myself, 1.5 times the previous term, which is 189, and we end up with 283.5. Okay, let's lay out our terms. 84, 126, 189, and 283.5. I analyze these. How do I get to the next one? Well, first try addition. To go from 126 to 84, I have to add 42. To go from 189 to 126, I have to add 63. So already what I'm adding is changing. So I know it's just not plus something. So we're going to go to multiplication. What do I multiply 84 by to get 126? And remember, you can check that by going the term divided by the term behind it, 1.5. All right, what about 126 to 189? Divide my terms, I get 1.5. Check this one. Once again, it's times 1.5. So it looks like I'm multiplying by 1.5 to get to the next one. That's a geometric sequence. Our rule for a geometric sequence is a sub n is equal to a sub 1 times r to the n minus 1 power, where r is that common ratio, how you get to each next term. Plug in what we know. I know that a sub 1, my first term, is 84. My common ratio is 1.5 to the n minus 1 power. And boom, I've got my explicit formula for this recursive formula. And I have to incorporate my skills of knowing how to write a geometric sequence. Or if that recursive formula would have given me an arithmetic sequence, I would have known how to write with an arithmetic rule. So it's important to remember those two. Remember, an arithmetic rule is a sub n is equal to a sub 1 plus n minus 1 times d, where d is the common difference. And there we're able to convert from recursive to explicit or explicit to recursive.